Logistic growth, part 2, an analysis of the differential equation. The differential equation that models logistic growth is given by dy dt equals ky times L minus y, where y is the population, L, a constant, is a limiting factor, and t equals time. We will assume in this video that k is positive. So, why does the differential equation give the graph on the left? Let's take a look at a few things. Since we have population, the population must be positive. If our initial population is less than the limiting factor, we see that L minus y naught is positive. This means that our differential equation will always be positive. Assuming that the initial population is less than the limiting factor. Now, if our slope is positive, that means the population is increasing. But if our population is increasing, then y is approaching L. But if y is approaching L, then our slope, as time goes on, must be approaching 0. So let's restate this. As time increases, we'll say as t goes to infinity, a couple things happen. We notice that the population increases to L, and then our slope goes to 0. So as time increases, our population increases, and our slope goes to 0. Now, you might ask, what if our initial population was greater than L? That is, what if our initial population is greater than the number that this region can sustain? Well, that simply means that L minus y naught is negative. And if this part of the differential equation is negative, then dy dt must be negative as well. Which means that the population must be decreasing but if my population decreases, that means the population is still going to approach L, which still means that the slope will approach 0. So regardless of what we start with, whether the initial population is less than or greater than the limiting factor, these two statements will be true. As time increases, the population will approach the limiting factor and the slope will approach 0. If we start with initial population greater than the limiting factor, we simply get the graph on top. Now there's one other really typical question that we like to ask, so we'll analyze that before we ask that later on, which will be the next video. What if we have the graph like this, and let's just assume that our initial population is less than our limiting factor. And we get this here. Here's our population graph. And the question is asked this way. At what population, not at what time, but at what population is the population growing the fastest? This is the place where the slope is the biggest. And we want to find what is the population at that point. So let's analyze our differential equation again. dy dt equals ky times quantity L minus y. I'm going to write this out as k times ly minus k times y squared. And let's break down this question here. At what population is the population growing? So the population is growing is the rate of change of the population. Okay, so I'm talking about this equation. And I want to know when the population is growing the fastest. That is, I want to find the maximum rate of change. So if I'm finding the maximum of something, I want to take the derivative of that something. Set it equal to 0, do a little more analysis, just to show that it's a max and not a min or a neither, and see what we get. So if I take the derivative of both sides up here with respect to time, we get d squared y over dt squared equals kl times 1 times dy dt, because my variables don't match, I need a chain out, minus 2ky times the chain out again. We already established above that dy dt is either positive or negative, so it's not going to be 0, so I will simply ignore it here, which gives me kl minus 2ky equals 0. K is positive, so we can ignore that as well, which gives us y equals L over 2. What does that mean? It means that the population in logistic growth is growing the fastest when it hits half of the limiting factor L.